In this video, we're going to talk about how to take partial derivatives. And I want to begin with looking at the graph of a function f of x and y. And I put a particular point on this function, the point f of x naught, y naught, some point that lives on the graph of this function. Now, what I want to imagine is that I am going to constrain my y value. I'm not going to change on my y value, but I am allowed to move in the x direction. That is, I'm constraining myself to living on a plane like this, where I have a fixed y value. Y has to be equal to y naught. But other than that, I can walk along my surface. When you take a surface and you intersect that with a plane, when you constrain it to be a specific y value, then when I cut away at that particular point, what I get is a one dimensional function. This is a function f of x and y naught. It looks a little bit like a downward facing parabola here. So what I have done here is I've taken a two-dimensional function, f of x, y. I have specified that the y value is fixed to be y naught. And what I've got out of this is a one-dimensional function. The output only now depends on x. So then, if I just focus entirely on this blue, on the f of x comma y naught, because this is a function in one dimensions now, I can ask questions like, what's the slope of the tangent line? And this is a question that we could answer back in first year calculus. The only difference is that we have this y naught being floated around. Now, this is the idea of a partial derivative. So the formula for a partial derivative is a bit of fancy notation. It's a sort of weird script thing that looks a little bit like D, and I pronounce it the partial of f with respect to x. That's what that del f over del x is another way of saying it. Typically, the partial of f over the partial of x. And I'm evaluating this at a particular point, x naught, y naught. And the answer to what this new thing is, these partial derivatives is it simply the old derivative of a one-dimensional function, that one-dimensional function f of x comma y naught, which is to say that after I plug in the y naught, that function only depends on x, and so I can take the derivative using the old d dx notation we used in one dimension, and it perfectly applies. Finally, I use the long vertical bar to evaluate it at x equal to x naught. So the idea is that I have defined the partial derivative of a multivariable thing to simply be the original single variable derivative when I plug in the value y naught. Now, this is the partial derivative with respect to x. We can also investigate the partial derivative with respect to y. So let's begin in the same place. I have the graph of my function, I have a point specified, but this time I want to restrict myself where the x naught value is fixed and the y value is changing. That is, I'm on a plane here with a fixed x naught and then all the values of y that are allowed. When I can take the intersection of that plane with the graph of my function, I cut away, what I get is nothing but the equation of a parabola again. It again looks like something that is a one-dimensional graph. Indeed, this blue portion can be thought of as the function where I plug in the value of x naught and I allow y to be arbitrary. So it has one now input that varies. It only has the input y variant. So from this, I can also ask what is the slope of the tangent line to this f of x naught comma y. And the slope of that tangent line is a question that we can answer in first year calculus. Hence, I'm going to define my partial differentiation in the following way. I will say that the partial derivative of f with respect to y, evaluated at the point x naught, y naught, that's what the long vertical bar means, is nothing but the single variable derivative d dy of this function that only depends now on y, this function f of x naught on y. And then finally, when you plug in the value of y equal to y naught, you've now figured out what is the slope in the y direction at this point, x naught, y naught. So the way I interpret this geometrically is that the partial derivative with respect to y is what happens if I walk along my surface, the graph of my big function, but with the x value fixed. In other words, it's the slope if I walked only in the direction parallel to y. Likewise, for the derivative with respect to x, the partial derivative of f with respect to x, this is what's saying if I move only in the x direction along my surface, how steep is it as I walk in that direction? Let me rotate my view a little bit, and I'm talking about the partial derivative with respect to x again. I want to try to dig a little bit deeper into this process. Recall that we had the 1 point put on the graph f of x naught y naught. But how was derivatives defined back in first year calculus? Well, the idea was that you would consider the slope of the tangent line to be a limit of the slopes of secant lines. The way we did this is that we would put a second point on, some other point that was also on the graph, and I will put on the point, it will be pink, labeled f of x naught plus h minus y naught. That is, it has the same y naught value. This just wasn't relevant in first year calculus, but nevertheless, what's changing is the x value. It's going from x naught to x naught plus h. Then when you have 2 points on a curve, you can define the secant line that goes between those 2 points. And then I can ask the question, what is the slope of that secant line? What is the rise over the run? And in particular, as that h value gets closer and closer and closer to zero, in other words, the 2 points get closer together, then the slope of the secant line is going to approximate the slope of the tangent line. So what we defined the derivative back in first year calculus to be, and to which we can extend it for these partial derivatives, is that this is nothing but the limit as h goes to zero of the rise over run for this secant line, the slope of the secant line. And the change in the y values, the rise is f of x naught plus h minus y naught minus f of x naught y naught. That's the change in the output values and the f values. And then the change in the input values, you went from x naught to x naught plus h, so you divide it out by h. So this is our formal definition of the partial derivative of f with respect to x in terms of limits. Let's investigate how to compute this thing. When I think about just the partial derivative with respect to x of, say, the function 3x squared y cubed, I haven't evaluated any specific point, so I want to do it in general. The way I'm thinking about this is that because I am taking a partial derivative with respect to x, y is fixed, y is constant. It does not change as I'm changing the value of x. And because it's constant, with respect to x that is, when I take its derivative, I can treat it the same way as if it was, say, 7 cubed here. In which case, 3x squared times 7 is easy. You just do the power rule, and you say it was 6x times whatever the constant was, in this case, y cubed. So computing partial derivatives is just a question of everywhere there's a y, you just imagine it's a constant. You take the derivative with respect to x as you would have done before. Finally, I've given the image where I put both of our two answers. At my particular point, I've shown the curve that happens when you move only along x and the curve that happens when you only move along y. There's two different tangent lines to those two different curves, and they represent the slope as you go in the x direction or the slope as you go in the y direction. But this leads me to a different question. What about all of the other directions? Parallel to x and parallel to y are interesting. But what about directions along the line y equal to x or any other number of directions here? So leave that thought for the future.